Okay, so I think we can start.
Okay.
Good morning, everybody. It is a real pleasure today to have here Debasis Ganguly from University of Glasgow in the UK. As you know, he's going to give us an invited talk about explainable AI and its societal implications. Debasis is a lecturer in data science at the University of Glasgow, and formerly was a research staff member at IBM Research Europe in Dublin. Debasis research activities over information retrieval and natural language processing, and more specifically is interested in applying semantic relationship between text units. For example, embedding the text unit into a vector space over reals for improving the various IR and NLP tasks. His recent research interest include application of multi-objective neural networks for bias removal of classification systems. So it is really a pleasure to have you here, Debasis, and thank you so much for giving us this lecture. Thank you.
Thank you, Nicola, for inviting me for play here and then introducing me as well to your students. So yeah, as Nicola told, that I am an assistant professor in the University of Glasgow, UK, and I mainly work on IR, and one of my interests is also explainable AI and applying explainable AI for information retrieval tasks as well. Before starting with the talk, I would like to say that, okay, so I'm looking for internships. So, if you're really interested to work on these cool topics like, say, explainable AI or explainable AI for IR, or for example, fairness, just come send me an email. We could take it up from there. We could collaborate with Nicola as well. So there are lots of opportunities that, if you're interested to work on this topic, just send me an email saying that you were interested. Okay. Okay, so the talk structure is something like this. So we're going to start with explaining why do we need explainable AI? So we'll be seeing that there's a shift from feature to data-driven learning, which actually leads to all these complex models. And then we'll need that. Why do we need explanations for these complex models? And then comes the trust issue as well. Like when we were talking about explainability, why do we need to explain systems? Because we want to put some kind of a trust to a system. Unless the system actually explains how is it coming up with decisions, we cannot really trust systems. So we'll see that there's connection between explainability and trust. We'll talk briefly on that. We're talking about types of explanations because depending on your data, your explanations could be of different kinds. I mean, if it's for images, then you will have different explanation units. If it's like text, you will have different explanation units. So we'll talk a bit on that. We will be specifically looking at one particular, so we won't have time to cover all the explanation algorithms in details, but I'll be giving you a brief introduction on one particular algorithm, which is LIME, which is one particular instance of a class of algorithms which work on local instances. So these are called local explanation methods. So we'll take a look at LIME, which is the simplest of them and the first one that was proposed among all these. So we'll take a look at that. We'll be looking at what can we do in future, because this is the explanations, the local explanations. It's all fine. When you talk about single instances and then explaining single instances, but then where is the bridge? Where do we need to go in order to explain complex systems? That involve real thinking. I mean, if we are to develop AI in the next 20 years, what kind of explanations should we be pursuing for those kind of more complex systems? So I'll be talking briefly on that as well. And then I'll be looking at one particular use case of local explanations for ranking. So which will be something similar to LIME, but applied in the context of information retrieval task. And then I'll be also explaining a different kind of explanations, which is so you have the statistical ranking models, and now we have the neural ranking models. So statistical ranking models usually work on the principle of some basic axioms. So we take into account the term frequency of a term, the IDF of a term. So we'll look at if you are building neural models, what kind of how are these axioms or how are these factors taken into account by those neural models? And then briefly, we'll touch about societal impacts as well. I don't know how much time will I have, but I'll try to cover everything that I can. Okay. So just to introduce the topic of explainable AI, think about Rick and Morty. So Rick is a scientist, but Morty is a teenager. So he's not that good at science as well. So he doesn't really understand the jargon that Rick says. So this is something that's similar to the whole situation of explainable AI, right? So we want to explain in simple terms to laymen. So laymen are, let's say, domain experts in some other domain, right? So they could be in the legal domain, they could be in the medical domain, but they won't be understanding the computer science terms that we use in our day-to-day lives, right? So Rick might be saying, for a question like, which movie should I watch? So Rick could be demonstrating how the recommender system works, but that's not going to help, right? So an answer like stacked layers of feed-forward networks over convolutions of word embeddings is not going to help. So we would want a more simple answer in such cases, right? So Rick will be confused in such cases because he won't be having a clue on what is the model doing, or what are the factors that is taken into account. So we need to explain things in terms of the data elements and not just the model elements, right? So this is the basic motivation for using explanations in AI. Okay. So why is this required? Because if you look at systems dating back 20 years or even more than that, you will see that systems were mainly developed in terms of features, right? So it was mainly like, they used to take as input features which were selected by humans. So for example, if you had to distinguish between images of cats and dogs, there used to be a list of features, hand-engineered features that used to be extracted from those images. So say, for example, the presence of something, the some feature, absence of some feature, right? And then humans used to look at them. Humans used to look at the training set and then figure out the difference between cats and dogs in terms of those features. And then this was more, so then the job of the machines were easier because the humans did all the abstractions, right? So it's the machines used to work with pre-abstracted notions of the data. But then, so what does that imply? That implies that the machines are left with human perception, right? So whatever humans are perceiving of the data, we are feeding that information to the machines, and the machines are just doing computation, right? So we could have placed full trust in the machines. If somebody used to ask us, like, why is this a cat and why is that a dog? We could have told them that, okay, so these are the features that were selected. Maybe the presence of whiskers, it indicates a cat. Presence of long ears, that indicates a dog, or something like that. So there was no issue with the alignment with respect to human perception in terms of the models, right? And then it was easy to look into what features. You could look into the linear regression coefficients, right? You can, and do something like that. So you can look into the feature importance for any classifiers, for any linear classifier, or even non-linear classifier. You could have done that. So you could have looked into the feature importance, and then the features actually correlated with human perception because they were designed by humans. But nowadays, with deep learning, we don't really do that. So we don't really input features. So we input the data. We input the whole data to our models, which means that we are leaving the model to build up some kind of task-specific abstractions of the data, right? So if you are trying to classify or distinguish between cats and dogs, the abstraction of the machine's builder will be different from if the task is something different. Let's say if you are classifying between different breeds of dogs, those abstractions will be different from between cats and dogs, right? So it depends on the task that you are trying to learn. And the machines actually learn these abstractions in a task-specific manner from the data itself. So which means that we want to know that what parts of the data are affecting the model's choices, right? So unless we know that, we'll always have this doubt about what the machine is learning from the data, right? It might come up with correct decisions, but then we won't be able to tell that if it aligns with the human perception of the task. Okay. So as I said, trust issue, and if the user, so if let's say if you're trying to explain, like let's say if you are trying to classify a disease type from some symptoms, right? And let's say you build an AI predictive system, and you want to deploy that to a hospital. But then the doctors will have all kinds of doubts, right? And why should I trust this machine? I mean, they could say that, okay, so if this works for this instance, I see that, but then what is the chance that it will be generalized well to some other instances as well, to some other diseases? So they would always have these trust issues, right? So you need to then explain that, okay, so for this particular disease, for this particular symptom, see that the machine is putting importance on these terms of the symptom, on these aspects of the data. And then probably they'll be able to see that, okay, so this actually aligns with what I would think. And then probably it will help him to believe that the system will generalize well to some other diseases as well, right? So this is all like, trying to convince non-AI experts, non-AI, so experts of other domains to be able to use AI systems, to be able to put trust into AI systems. Okay. Explanations can be of two different types. One is at the prediction level. So I'll be talking about these local explanations and stuff. So this actually explains one single instance. So for image classification, if there are two classes into which you want to classify images, let's say cats and dogs, you will look at one particular image instance, either of a cat or of a dog, and then point out that these are the data instances, or these are the sub-instances of that data on which the model puts emphasis. And then this is how, so you'll try to find a correlation of what a human would do for that one particular instance, right? Whereas if it's at the model level explanations, then you need to look at a subset of instances, right? And then the idea would be that you present diverse instances, and then, with the prediction level explanations for all of them. And then the argument will be like, see, that this works for many different kinds of diseases or many different kinds of images, right? So if you are showing as explanations all the images of a cat, even then, there could be questions on how does it generalize for dogs, right? So you should ideally try to select as many different diverse examples as possible, and then show that the local explanations are actually consistent for all these different types of instances, right? Okay, now just look into it visually. Like, so whatever I've been saying, it really helps if you can visualize the stuff. So let's say, there is a model, a deep learning model, which just takes as input the text of, some symptoms of diseases, right? And it predicts a probability distribution over the diseases, right? So let's say it says that, okay, so in this case, the max likely is the flu, okay? So then, you could say that, okay, why is this flu? So that's what the job of the explainer is. Like, why does the model believe that in this case, with this given symptom, this disease is flu? So we then look into, so the model, what you do is, from the explanation point of view, is that it will be highlighting particular pieces or particular segments, highlighting different aspects of the document, right? So in that case, sneezing, the presence of the word sneeze, the presence of the word headache, and the presence of the word no fatigue. These could be important indicators that the disease is actually flu. And this, if you show that to a doctor, he will probably see that, okay, so I would have been looking at these particular aspects as well. If I've presented with this list of symptoms, I would be looking for these particular aspects in order to come to my decision whether it's a flu or not. So in that sense, it aligns with the human perception. Okay. Similarly, let's say another example, if you have to classify emails into, in this case, I think the class is, it's atheism or not. So in that case, let's look at this. So there are two different models. Both of them predicts that it's in the class atheism, but one of them puts importance on terms like God and something else, but even like putting importance on the term God or the absence of the word God, whatever in this case, because that's something corresponds to atheism. So that is more relevant, and that more aligns more with human perception than the other model. It looks into terms like postings and host. You all know that the email headers, right? So maybe the model does well for this particular task, for this particular test set, but will it generalize well? Probably no, because there is no alignment with what a human would do in this case, because it just could be a fluke, right? You just could be, just for this data set, there are some characteristics that lets the model predict that this is a theism, but that's not going to be generalizing well. So this gives us insights into the model workings, right? So in this case, you can definitely say that model 1 is definitely better than model 2. Although they might achieve similar accuracy values, but still this will be a different dimension to look at to evaluate models. And for images as well, so let's say this is an object detection task. So the input is an image, and then you need to classify that what kind of objects are there in the image. So in this case, one of the objects is, it predicts that it's an electric guitar, but clearly it's not. It's not an electric guitar, it's an acoustic guitar. But the model says that, okay, so if I focus really on this part of the image, then probably, it's not wrong to say that this could be an electric guitar, right? Because you are not seeing the other parts of the image. So in that sense, even though the prediction is wrong, you could still say that even for a wrong prediction, I was looking into the actual relevant sub elements of my data. So that actually builds up a trust. So their trust doesn't need to be perfectly correlated with accuracy. So in that case, the model is wrong. But even if you see from a practitioner's view or from a non-domain expert's view, and if you see that the model is actually focusing on the actual relevant parts and then predicting its decision based on those sub-instances of the data, then that kind of builds up a trust as well, even though it could be wrong. The model could be wrong in certain cases. Okay. And then I was saying that, okay, so explanation units are different for different types of data. So we already had looked at some of the examples in the earlier figure, right? So we're looking at that for text. These will be like, segments of words or sequences of words from a document. It could be like, for example, this one and this one, they were sequences of words. For images, they could be regions within an image. And, okay, sorry. And for something else, it could be something, so we could also have multimodal information as well. And then we could be looking at other types of data on which the instance is going to be different, on which the explanation unit is going to be different. So let's say, for example, a visual question answering data set, right? Or visual question answering task, in which you look at a particular image and then there's a question on that image, right? So in this case, the question is, how symmetrical are the white bricks on either side of the building? Okay, so if you want to answer this question, so the ground truth is vary because it says that it's symmetrical actually, and the prediction is actually very symmetrical. But is the model actually working well? So then to be able to analyze that, you should be able to figure out that, okay, so what parts of the question were actually important in coming up with the prediction, right? So in this case, the model puts more importance on how, okay, but not on symmetrical. So that's not a good thing. So symmetrical should have got a high importance value, which is not the case. Breaks, so that's good. So breaks is like given some kind of importance. On either side, okay, either is not that much. But, if the word symmetrical is not really taken into account, so there could be issues in trusting the model's predictions, right? So that's what you need to find out. So you need to find out, so it's just about these white bricks, right? And even white. So white is not really given some importance here, right? So it's more likely that the model is not really aligned with what a human would do. Because as a human, you'd ideally look into these bricks over here, right? And the same you can say for the image as well. So this is one part of the data with the question. You can also look into the image, and then just like we had looked into this image, right? So you could highlight specific portions of an image. You could do the same for a visual question answering task as well. So for the image, you could highlight specific portions of an image. And for the text, you could highlight specific words in the text to be able to see if it aligns with the human perception. Okay. Okay, and then you could also apply explanations for other kind of tasks like knowledge-based linking or like link prediction tasks. So if I ask, so this, let's say there is a knowledge base and there are questions asked on this knowledge base, like who is the first lady of the USA? So if you want to explain this, explanations in this case will typically be paths, right? So paths that actually make you, that actually lead to the inference of the correct answer. So in that case, the inference path will be like, who is the current president of the US? And then who is his wife? And then, if the model is predicting a wrong answer, then probably, you could trace the paths and then exactly see where is this getting it wrong. Like, for example, if it's not yet updated in the knowledge base that Donald Trump is no longer the president of US, that Joe Biden is the president of US, then these are the easy things that you could catch, right? So if the model is predicting a wrong answer, so you could really trace back and see that what exactly needs to be updated in the model to be able to come up with the correct answer, right? So in this case, you just need to remove that link and then put a different link to the president of US, right? So once you do that, then you get the correct answer, else you get the wrong answer. Okay. And then there's something called counterfactual explanations, which is more useful in recommendation systems and information retrieval situations as well. So counterfactual explanations is like, okay, so if a recommender system is recommending me some movies, usually it does that based on my history. Okay, so my history and maybe some other similar users' history as well. So the point is, I want to know why am I being shown? Let's say it predicts just one top recommendation item. So the question I could be having is like, why am I being shown this recommendation, right? So in that case, a useful thing to do would be to argue that, okay, so if I hadn't watched these movies in the last week, how would my recommendation have changed? And if that makes sense, if the recommendation algorithm is saying that, okay, so if this movie wasn't there in your history, then I would have recommended you something else. This kind of recommendations can actually help in figuring out. So it's some kind of a probing, right? So you are kind of probing the system and then asking yourself like, okay, so if this wasn't there, what would have been the output? If this wasn't here, what would have been the output? So then it actually like helps the user to understand how is the model working in general. So say, for example, if I'm being recommended Scarface because I had watched Godfather and Irishman, that makes sense. And if the algorithm says that if I hadn't watched Godfather, then probably, or if I hadn't watched Irishman, then it would have shown me Godfather 2 as my recommendation. So which kind of makes sense, right? So this is how you kind of understand how the model works. And you can also apply that for classification tasks as well. So if you have a decision boundary, you could try to shift your point to somewhere else in terms of, so when you shift a point, it means that you are changing the features, right? And that's how, you could kind of assume that, okay, so if you are too close to the boundary, and then if you're changing the feature, then your classification can change, your prediction can change. So that kind of lets you understand what's the decision boundary of the model, right? I mean, this is a bit difficult to visualize, but then this is like, that's the idea behind it. But it's well visualized for the discrete case, when you have like actual presence or absence of items in your history. Okay. Now, what are the desirable characteristics of an explanation model? I mean, it has to be interpretable because the explanation units, so we have been looking at words from a document or sequences of words from a document. We have been looking at image regions for images. So they actually make sense because you can look into them, and then that is how we actually think, right? So we look at the presence of words in a document. We look at regions within an image, right? So these are interpretable from a human perspective. If it had been something else, then it would have been difficult to like actually align with human perception. So firstly, it has to be interpretable. Local fidelity means that it has to be locally faithful. That is, so if I am suggesting that these are the important regions within an image, so which means that if I input only that part and mask out everything else, that prediction should also be consistent, right? So let's say, for example, again, get back to this figure here. So the idea is that, okay, so if my explanation algorithm is saying that this is the region within an image on which the model puts more importance, then if I mask out everything else and only input this one, I should get this prediction, right? So the explanation model is faithful if I input this particular masked image to the explanation model itself and get back this predictive class, right? If I don't get it, then the explanation model itself is not faithful. So the explanation model itself has to be faithful to whatever it's predicting, right? So this is more like the accuracy of the explanation model itself. So you want that to be high as well. And it has to be model agnostic, right? So the explanation model itself cannot assume anything about the black box model. Because if it does, then for every black box model, you need to come up with a new explanation mechanism, which doesn't make sense. So all the explanation methods, they are standalone methods. Say, for example, LIME, SHAP, L2X, they are all standalone methods that can work on any black box models. They can work on convolutional nets, they can work on transformers, doesn't matter. All they assume is that there is a model with some input and some output. They treat everything as a black box, which any explanation algorithm should do. It should not assume that the models are gray boxes or white boxes. It just has to assume that they are black boxes. Okay. Okay, and then what usually is the output of an explanation model? I talked about sub-instances from your data. So basically, it's just that, right? So how it works is that, okay, so it transforms every input X to a different space representing the feature importance, right? So it could be, so you need to decide what are your features. You need to decide that, okay, so for images, I am going to work with pixels, or I'm going to work with 3x3 blocks of pixels, or 5x5 blocks of pixels. For text, I'm going to work with words, or bigrams, or 3 grams. So that needs to be defined, or sentences. So that needs to be defined. So these are the atomic instances of, or sub-instances of your data, right? So that has to be fixed. And then your explanation model can work on that assumption. So it comes up with feature importance weights for all those sub-instances or atoms of your data. You need to define the atoms in your own way for a particular task, okay? So if you are dealing with 3x3 blocks of pixels, you'll get weights for all those 3x3 blocks of pixels from an image, okay? Okay, now let's look into one particular algorithm line. As I said, I only have time, won't be having time to cover all of them. But everything, all of them in principle are similar. So philosophically speaking, they use the same or very similar ideas. So the whole idea is like, you have a black box model that's going to give you a very complex decision boundary because it depends on the data, right? So it doesn't make use of features. It makes use of the data. So the abstractions that it's going to learn from the data is going to be a complex one. But we want to approximate that with a simple function. So remember that any explanation algorithm that I talked about, that I will talk about, works on local instances, right? So these are all local explanation models. So they work on one single instance. So you need to explain one single instance. Okay, and let's say that instance is this one. Can you see my mouse? Probably no. Okay, so let's say this is the instance here. And the prediction, so there are 2 classes here. In this case, the red and the blue. So in this case, let's say the prediction is red. So this is the point that you like to explain. Okay. So then what is the next step? The next step is that we are going to sample pseudo instances, right? So again, coming back to the example, so that center cross, the red cross, that could be this particular image here. This image for which I want to explain that why is it being predicting as electric guitar. So that is the task of the explainer model, right? So I want to sample similar images to this. So what do I do? So then a very nice idea is to mask out different regions from this image and then create all the pseudo instances. These pseudo instances will be similar to the real image, right? Because all you are doing is like masking out a few pixels here and there. But if you compute the inner product of the 2 images, there will still be the very, very high inner product, right? Because they're still similar. That is what we do. So depending on how much we mask out from certain regions, these similarities will vary, right? So this gives me a neighborhood of pseudo instances around this instance, right? And then, so once I mask out and then form the pseudo instances, I need to see how does the black box model work on these pseudo instances. And depending on the black box model's predictions on the pseudo instances, I will be able to say that which regions in the image were important and which regions were not. Again, try to visualize the idea, right? So let's say again for this image, this is one pseudo instance, right? So I leave out everything else. I only use this part and I mask out everything else. So the thing is, if everything else is masked out, then how is the model behaving? So if I mask out something that was important, so in this case, it was important that there was a dog in the image, right? I had masked that out. So if I'm masking that particular piece out from the image, my decision is changing. So let's say, again, coming back to this figure, if I mask an important part of my data, maybe I'm not predicting that to be in the red class, I'm predicting that to be in the blue class. So what does that mean? It means that that part that I masked out was really important for the classification, right? Because it changes your prediction drastically. It makes that to a different class. So which means that, if this is going to happen, so then you are going to accumulate all these importances from all these. If you're pruning out and then it changes the decision boundary, then it's important. And then if you're aggregating these important weights over all these different samples, then you get to estimate the importance of those atoms of your instances, right? So this is the basic idea that Lime uses, okay. To speak more formally, in this case, theta z is the black box model. Theta is the black box model, and z are these instances of the pseudo instances from the neighborhood of x. X is the actual instance that we want to explain. So in this case, we would learn another parameterized function, a simple linear one in this case, because theta is not linear, it's a deep model, but we'll be learning just one single layer of parameters. That's called phi here. And then the job of the phi function will be to approximate as closely as possible the predictions of theta, right? So imagine that this is a simple linear regression, right? So you get these real number values or the weights from theta. Let's say, it's a classification problem, so you get the softmax probabilities. You just want to approximate that as closely as possible with phi. Phi is a simpler model, right? And then once you do that, then you could look into the linear regression coefficients and then explain how this output all the weights of those sub-instances, right? So that's the idea of Lime. Okay, and then let's look at one example where, so this is also important because if you have a multi-class classification problem, then it could be the case that if you look in the softmax distribution, let's say in this case, the highest was electric guitar, but then the next one was acoustic guitar, the next one was Labrador, right? So it's not that you just have one single class, but you have a distribution of classes in softmax. You could try to explain all of that. So you could say that, okay, so if my explanation is electric guitar, you could fit Lime and then get a different set of weights. So in this case, electric guitar, the Lime algorithm puts more importance on this part of the image, which makes sense. If you say that, okay, so my model is predicting acoustic guitar, Lime actually then goes and fits it and then assumes the importance weights into something else, right? So it says that if my prediction is this, then these parts of the image are important, which also makes sense because in this case, acoustic guitar, you take into this part, right? So it's not an electric guitar. It's this big thing over here. And then if it says it's a Labrador, then the Lime algorithm actually goes and finds out that, okay, so this was an image of a dog, right? So your explanations, you can tune your explanation algorithm as per your predictions. So you could have multiple predictions, if it's a distribution of a softmax, and you could fit Lime for all of them separately, right? And that gives you a more complete picture of what the model is doing. Okay. Okay, and then I talked about that. Okay, so these are all per instance explanations or local explanations. And then there's also something called overall or global explanations, right? So global explanations is nothing but then you need to find out a subset of instances that you want them to be diverse. And then you want the explanation vectors. So remember that all these, whenever you are estimating the explanation weights, they're in terms of the sub instances of your data or atoms of your data, right? So all you need to do is when you want to explain a model's overall performance with respect to a particular task, you need to provide examples where the explanation vectors are different, right? So again, let's say F1, F2, F3, F4, F5, these are all your explanation features, that you can fix, right? So this could be all 3x3 blocks. This could be word 3 grams, something like that. And then you have your instances. And then you could find the optimal subset. And this is a submodular algorithm, which means that you can apply a greedy algorithm to find the optimal subset. And then you will always be not that far from the actual, from the true optimal, right? So if you apply something like an epsilon greedy strategy, then there has been work which shows that there is approximately speaking, you will remain within that bound, with some value of epsilon. So that's something that you can do. So you can try to select. So the objective here is to optimize the subset selection process so that I select a subset of instances with diverse explanation features. The thing is, if you already have selected the row number 2, probably there is no point of selecting row number 3 because it's the exact same explanation weights, right? Probably also not explanation row 1 because it involves this overlap with F2. But if you're selecting this one, then you are minimizing the overlap between the features, right? So this is something that you can do to diversify the set of explanations. And then when you're presenting your model, you could say, okay, so look at this particular instance and look at this particular instance. For this case, I was putting importance on these features. And for this case, I was putting importance in these features. And they're different. So you get a whole diversified view of your models working. Okay. Okay, now let's look into some complex reasoning tasks. I mean, whatever I had said till now, these are all very simple forms of explanations because you first decide on the atoms of your data instances and then find out the weights for those atoms in your instances, right? But when you talk about AI, I mean, if you really want to see that, okay, what reasoning capabilities AI has got, so then your explanations can be a bit more complicated, right? So simply looking at attention weights in some cases may not be sufficient to actually put trust into a model. And this is something that we will look at, with a particular toy example. So let's introduce Vanguard problems. So Vanguard problems are those cases, where there are 2 sets of images, one on the left and one on the right. And then there is some latent characteristic that actually separates out the left images from the right images. And you'll be asked to find out that why is the images on the left different from the ones on the right. You don't know that, but you need to explain it to a user, right? So in this case, this is a very simple Vanguard instance where you can see that all of these are like big images on the left, and here they are small images. Why? So you might also say that, okay, so some of them are white, some of them are blacks, but then you also have black images on the left. You also have white images on the right. So white or black is not a good explanation for this case. In this case, the correct explanation is small or big. So you need to then argue, right? So you need to start with some argument and then maybe backtrack your argument and then modify it and then find out the optimal combination. So this is a complex reasoning task that's being involved. This is a bit difficult. So why do you think that the left images are different from the right images? Because in this case, again, there's a mixture of both small and big images on figures on the left and right. But in this case, it's about the homogeneity, right? So in this case, homogeneity was not a factor. All of them are homogeneous because the left ones were small figures, the right ones were big figures. In this case, there's a mix and match of both. We don't have the colors here. The colors are all white. But in this case, the images on the left, they are comprised of a mixture of both small and big. Whereas in this case, no, it's just big images, right? But again, the argument whether it's circles or triangles don't really make sense because you have a mixture again on both sides, right? So this kind of reasoning tasks are different, and Vanguard problems can also be very difficult, even for humans to solve. So if I show you this set on the left and this set on the right, I mean, usually, it's a very hard instance to solve, because in this case, there is nothing about the atomic attributes of the instances that makes sense. It's about the abstract or derived feature about the cardinality of something. So in this case, the left-hand side is an abstraction for 3, and the right-hand side is an abstraction for 4, because you have 3 lines here, you have 4 lines here. Yeah, again, you have 3 lines here. Here you have got 4 dents or 4 outdents, right? Here you've got 3 figures. Here you have got 4 tracks or something, right? So this is very difficult to figure out because this has got nothing to do with the actual sub or the atomic attributes of your data, but this is some abstraction that you build from those instances, right? So Vanguard problems can be difficult. So in this case, if a machine used to solve the Vanguard problem, it has to come up with the explanation that I could see that the left-hand side is an abstraction for 3, and the right-hand side is an abstraction 4. And that's very difficult to do. So all I'm saying that in this case, if you're just putting attention weights on the instances, on the images, they're not really that helpful to really see what the machine is doing. So to look at an example, if you're just putting attention weights here, it doesn't really tell you anything, right? So it doesn't really tell that, okay, so it's the homogeneity factor that was really taken into account by the model when it says that the left-hand side is a mixture of big and small figures, right-hand side is just big figures, right? Okay. I don't think I have much time, so I'll be trying to finish it as quickly as possible. Okay. Now let's look at some information retrieval tasks. We had looked into classification tasks for the time being. The concept of line or these local explanations can also be applied for information retrieval tasks. And how is that? Because again, we try to recollect that we were masking out different regions from an image, or for a text, we're masking out words, and then trying to figure out the importance of words. So you can do the same for neural ranking models as well. So all you can do is, let's say if you have got a top list of documents, so you can take one document and then you can form pseudo instances of the document, right? And then you could mask out words from the document and then compute the relative change in the scores of the document. So if you are removing an important word from a document, ideally, let's say a query word. If you're removing a query word from a document, you expect the score of the document to change significantly. If it was ranked at, let's say, rank 2, and if you're removing the query words from that document, or one of the query words from the document, maybe the rank is now 10, okay? And the score has now dropped. So which means that if the score drop is significant, this means that those words were important, right? So essentially it's LIME applied to the context of information retrieval task. Okay. Why do we need this? Because we have complex models now. It's not just it's not just like BM25 or LM-Dirichlet, where you have a closed form expression of elements involving the term frequency, the IDF. It's not like that, right? So we are just training models on instances where we know that, okay, so for this query, this document is relevant, and we have pairs of that kind, numerous pairs of that kind. And then we are learning parameters to be able to optimize it on that data set, right? So these are complex models, parameterized models. And then we don't really know how they work, but one of the ways to visualize how it works is to do something like LIME. As I said, you remove terms. So again, you form pseudo instances of these documents, right? So you sample, let's say 50 documents by removing terms at random, and then compute the importance of terms from those documents, right? And that tells you, like, why is this document was retrieved at that rank? Because if you know that the score was quite high, you can attribute the reason to these sets of terms within that document. Okay, yeah, so this is exactly Lime applied to the context of information retrieval. I won't be going through all this. You can read my Sakaya 2019 paper if you're interested. I don't think I've got time. I'll just.
In any case, there is plenty of time up to midday, so you can relax if you wish.
Okay, okay. Yeah. Okay, so what we did in the paper was like, this is Lime. So Lime actually, so I showed you that figure, right? So I showed you that figure. I didn't talk about that explicitly, but then if you had noticed or not, but then these shapes are of different sizes. But why is that? So we want to weight the contributions based on the distance of that pseudo instance from the real instance, right? So let's say, again, going back to the image. So if I had masked out a part of the image, and let's say, its similarity with the original image is lower, then we'll put less importance on that pseudo instance. Whereas, if for a different pseudo instance, if it's quite similar with the actual instance, then we'll weight it more, right? So this is what this figure indicates here. The size actually determines the relative similarity of that pseudo instance with the true instance. So you can do a similar idea here as well for ranking tasks, where D dash is a pseudo document which you obtain by removing terms. And then there are some documents, with the TF-IDF factorization, there are some documents that will be more important, that will be more similar to the actual document, to the original document, right? And then in the Lime estimation, you could have this kernelized form, where to have e to the power minus distance of that, right? So it's a decaying function, where if the similarity decreases, then the importance weights also decrease. So this is some kind of a weighted regression that you can do. That's what Lime does as well. And then for the sampling part, so when I'm saying that you can remove terms from a document, so Lime didn't explore this, but we explored that in the context of IR. You could either remove terms uniformly. That's what the Lime algorithm does. So it does everything randomly. But in the context of IR, maybe uniform sampling, removal terms in a uniform manner is not that good. So you could actually do something like bias sampling, because that in IR, we know that some terms are more important than other ones, right? So a term just got a very low TF-IDF or a very low IDF, say, for example, it's not that important in this context, right? So we could have this bias sampling where we actually find out the TF-IDF weights, and then normalize them, and then make it more likely that you select terms with higher IDFs. Or you could have mask sampling, sampling in a chunk, right? So when you remove things, you don't remove isolated terms, but you remove terms in a chunk. So you can define a window size, and then depending on that, you remove that whole chunk at a go, because then it takes into account the context of a term. So this is something that we tried out. Okay. And then, okay, so if you look into the output, so I think this query was about counterfeiting money. And you can see that the query words have really got a high importance here, because counterfeit has got the highest value. Money has got a very high value as well. Something like agent has got a low value, but on the higher side, right? So magnitude is high, so which means that the absence, so the presence of a term agent, so it tells you about the absence. So it says that the absence of the term agent is important. So which is a useful insight. I mean, this is very difficult to figure out actually, that what really was important to bring this document to the top ranks. So it says that, if it doesn't if it doesn't have the term agent, then it's actually like better to actually improve the rank of this document. Similarly, I've got a high term here, trade. So trade is, again, presence of that word trade, it actually tells you that you should, that document should be scored higher. Okay, so this is what we did for the paper. I don't think I need to go into further details. Okay, so let's talk about another paper. So till now we looked into finding out the weights of the sub-instances of your data, right? Or the atoms of your data. Now, you could also say that I want to find out the importance weights of atoms of a function. So in IR, let's say we have a scoring function, a parameterized scoring function, but then we know that this function eventually is a building block comprised of 4 different factors. One is the TF of a term, one is the IDF of a term, one is the document length, and one is the semantic similarities between terms, right? So, and there could be other factors as well, but let's say these are the 4 basic ones. So if these are the building blocks of a function, and if I assume that every function is a combination of these, some linear or nonlinear combination of these, then can I actually find out the contribution of all these factors in a function? So that's what we did. So essentially, again, line, but applied in the context of trying to figure out the importance weights of the functional elements and not the data elements. So that's the idea. So in BM25, it's a closed form expression, but then we all know that it's some function of term frequency, IDF, document length, and the semantic similarity is not explicitly a part of the formula, but maybe there is some component, right, that actually determines the BM25 scoring function. So that's what we want to figure out. So we want to probe into ranking functions and then want to see the relative contributions of all these 4 aspects of a function. Okay. So again, so in neural models, you basically learn that with triplet loss. So you have examples of relevant documents, and you have hard negatives as well. You have negative information as well. So this is something called noise contrastive estimation that we do and learn the parameters, with the triplet losses. So again, this is something that's completely, it doesn't take into account all these factors. It doesn't take into account DF, doesn't take into account IDF, document length, semantic similarities of terms, explicitly no. So then, we could look into a function like this. So we could look into Colbert, we can look into Mono-T5 or some other neural models, let's say TRMM also. And then we could try to probe into them as a black box and then figure out what are the relative importances of all these 4 factors. Okay, so which we do. I am not going to technical details of all this, but then look into the equation right at the bottom. So it's again a loss function inspired from Lime. Where you have this, you are trying to fit a model that closely resembles your black box model, right? So SWD is the parameterized model that you want to explain. And then theta, these are the components of, so theta is a 4-dimensional vector here because these are the components for TF, IDF, document length, and semantic similarity. So these are the 4 numbers that you want to estimate. The coefficients of these numbers is going to characterize your scoring function. Okay, so that's what we do. And yeah, we can look into the paper and to see some results as well. I haven't included the results in these slides, but you can do that later on. Okay, and then let's conclude this by talking briefly about some societal impacts of expansions, right? So if I say, is a model fair? So expansions is, in my opinion, is somehow related to fairness as well, because there has been a lot of work that's been done to try to make models more fair. These are all parameterized models that learn directly from the data. So we want to have a control on what to learn from the data, right? So I think that as a model practitioner, if you can say that these are the atomic instances of my data on which the model is putting more importance, I think that could be a way to actually build up fair models, right? So people usually use adversarial learning to make models more fair, but I think there's a close connection between explainability and fairness, because if you can actually see so explanations will give you typically model characteristics, right? On local model characteristics. But then the fact is, if you can look into those outputs, and then if you can figure out that, okay, so maybe this part of the model for this data, it puts more importance on this, maybe that's what leading to a bias. So if you can make such a map, then it will be easier to build models in a way that you want to rectify that, right? So there is a connection between explanations and biases of a model. And yeah, as I said, visualization like this can actually help in mitigating the biases. Okay, so I don't think I have more slides, so I'll just conclude. So we have looked at explanations in AI, that we have looked at it's a medium to build trustworthiness with end users, and that it's a tool for practitioners to develop more effective models, right? So firstly, you convince people that, okay, so I have come up with this model, why should it be deployed? Why is it a good model? It actually helps that if you show that to domain expert and then show in terms of his perception, right? So you show that, okay, so this particular disease classifier, it actually puts importance on these terms, which is something that you would have done too. So this model is good. So that's one of the uses. The other uses is like if you're an AI practitioner, you can look into the model working characteristics, right? So you could say that, okay, so this, I want to retune my model. I want to build a newer version of my model because it puts importance on all the wrong instances of my data, on the wrong atoms of my data, right? So that's not going to work out. So I need to, in order to build more trustworthy models, I need to do something else. So it's also useful for AI practitioners. So the current state of AI explanations is that it's still limited to attention weights over the fine-grained units, pixels or words. But I told you that, okay, so for complex reasoning tasks, so that may not be the way to go. And then there are open questions like, what will be the fine-grained units of the atoms for complex learning tasks? So one of them could be the complex arguments. One of them could be, I don't know, reinforcement learning. So things like if it's not a simple classification task, if it's not a ranking task, then what will be my explanation units? This is something that's still an open question, which you all need to think about. So these are all, and then the explanations in some cases, it may also need to involve multimodalities of data, right? So we looked at one single example of visual question answering, but then again, attention weights, you could put attention on the question, you could put attention on the regions of the image that involves the visual question answering. But then where is the bridge? Where is the link between the two, right? So these will be different explanations, but then it doesn't really link, right? So I think that's also a gap that needs to be addressed. Like if it's a multimodal task, how are you going to bridge the gap between the two modalities of the data in terms of explanations? So explanations in certain cases could also involve like explaining the link between the two types of data. Okay. And then road to the future is that we need to come up with more abstract and easy to understand explanations in natural language, maybe. Like, for example, for the Vanguard problem, as a human would explain, like, why is the left set different from the right one? Maybe we need to come up with algorithms which do the same. So coming up with explanations that's in natural language, and we all understand that, right? So as we would explain something to other person. So I think, even models can be made to do that. But that is more complex because then you need to explain things in natural language. Apply under interactive decision-making environments like reinforcement learning. We don't really know how that works, right? So if you were to work your way out through a maze, that's a situation where you don't have enough information from the environment. Your environment is probabilistic, and it's a sequential decision-making, right? So how are you going to even explain that? The working principle of a model, we don't know. We need to think about all this. And then apply for unsupervised and semi-supervised learning settings. So this is also an open question. So yeah, I'll conclude my talk, but then any ideas on this? So go through my slides, and then if you are interested in this, let me know. We can collaborate definitely with Nicola and then work on this. Thank you. And if you have any questions, we'll be happy to answer. Thanks.
So guys, any questions? Also, people on Zoom or on YouTube. So I start with a question, Debasis. What about the performance of these explanations? How good are them? How do you evaluate if they are useful for the user, or also, I guess it depends on the kind of user, if it is a technical user or a general public, etc. Because here you have characteristics, but
That's actually that's actually a very good question. So okay, so if you want to evaluate this quantitatively, then the way to do is the local fidelity, right? So that gives you a consistent measure of how consistent is your explanation. So you are eventually, you are trying to fit a function to your black box model, right? So the first thing that should happen is that it should have a close fit. So that is a way to, that's the first test, right? That if my explanation model is actually close to the black box or not for this particular local instance. So locally, is it approximating the boundary well enough? Again, if you look into the line figure here, so you are estimating this line, right? And then, you can clearly see that the line actually approximates the region of the decision boundary around this point. Because, although it's a very complex and jagged boundary, but around this particular instance, this is more like a line, right? So it's very close to being a line. And then you actually find out that line. So this is, in this case, it's pretty consistent with the black box behavior locally. So that's one of the things. The other thing definitely is, when you want to aggregate your instances and then present this to the user. So that's one of the other things. And then people also do user studies. So they actually, that's a qualitative evaluation. It doesn't have numbers, but then you could say, you could have a questionnaire and then ask a user, maybe it's a task-driven study, where you ask them some questions that was it easier for you to complete this task, provided that, we have a baseline system where you don't have explanations, and here you have a system which offers you explanations. Now, does that help you to finish your task in certain ways? Another thing is the trustworthiness, but then again, it's difficult to evaluate, right? I mean, you could just ask users that, do you trust this model? Which one would you trust, right? So you could have, a situation where you want to choose between 2 or 3 different models. And if they end up choosing one, which offers explanations, and they end up believing that's more trustable, then that's also a way to evaluate, right? So quantitative evaluation, fidelity is the only way to go. But then for qualitative ones, user studies, maybe task-driven or maybe simple questionnaires. But yeah, there is no consensus on this, unfortunately.
Thank you very much. Any other questions? Yes.
It has been discussed or I can come near to the desk. I don't know, instead of screening. Well, I tried. It has been discussed the importance of explainability, especially in decision-making systems. But there are some situations in which we have a sort of different decision-making. I'm thinking about autonomous driving, like the moral machine experiment, in which we have a sort of no choice.
I lost your voice. I can't hear anything. I can't hear you. Yeah, now I can.
You
Yes.
can?
Yes, yes.
Okay, yes. It was a question from the classroom. So the question was, okay, you explained explainability for the in decision support systems, if you like, in easy cases, but relatively easy cases. But what happens if you have ethical implications, cases where you need explainability for ethical implications, and the usual suspects come to mind, like autonomous driving, medical decisions, etc. Yeah. Are these techniques still good and appropriate, or you have to resort to something different?
Yeah, that's a very good question. So that actually brings me to explaining about this reinforcement learning situation, because autonomous driving is a reinforcement learning situation, right? So you need to make sequential decisions over a period of time. Medical decisions, that's more like a classification task. That will be all independent decisions that you need to make. But when it's autonomous driving, it's a sequential decision making because it depends on the context of what you had decided before, right? So I would like, although there is no such work on this, or maybe there is, but I'm not aware of them. Maybe they are recent works. But I think that you need to chunk up your decisions into certain situations, right? So if like take for example driving a car, so the decision of let's say if there is a bend coming up, right? So you need to chunk up your decisions along those lines, something that we interpret as humans. So we need to have these basic abstract chunks that we can process, right? So in this case, if you're taking a turn, you need to look at, for that chunk, you need to look at the sequence of decisions that a human would take and maybe try to find out some correlation with respect to what a machine does while taking that turn, right? So if you're, I think the locality in that case would have to be extended to not just one single instance, but to a chunk of decisions and the environment inputs that the model is processing. And then again, like I don't have a definite answer at this stage, but I think you need to measure some kind of a correlation between what a human would do when taking a turn and then what the model is suggesting. But then looking at one single picture, one single image, and then attention weights is not going to help. So there has to be elements combining all of that. Attention weights, definitely yes, but then it has to be linked with something else. What will be that something else? I don't know. But it's a very good question, and I'm sorry that I don't have an answer for you at this stage, but it's an open question.
Thanks. Is the answer?
It's clear.
Okay, so any other questions? Also open questions or curiosities on Zoom? Okay, I have another one,
Yes.
which maybe is a bit technical. You were showing the histograms before where you were explaining how the match worked, which words were important. Yes, these ones. And okay, this is explainability, but would it be possible to use this kind of weights or features for query performance prediction?
Yes, I mean, query performance prediction with respect to a particular model, yes. Because all you are trying to do is you are trying to put importance of the terms for a particular query, because this has this local effect to it, right? So this is not just a particular query, but one query and one document. But query performance prediction is one query. So it is local, but then it's a bit more than local with respect to a document, right? So it's local with respect to a top set of documents. So yes, I think if you are figuring out the importance weights for for each document, you are finding out what are the terms that are important to be able to score the document highly enough. You can do that. So you can look into the histograms of the top 10 documents, say for example, and then try to argue along those lines. I mean, maybe some heuristics based on that, or maybe you could use them as features. I mean, if you have a training set of relevant items for queries, let's say the MS Marco collection, so where you have a big training set of queries and relevant documents. So you can compute the MAP values, right? Or you can compute the MRR values. And you have this pairwise decisions of whether query A is better than query B. So you have these pairs. So I think if you're using these features from your top documents for those queries and feeding that into a supervised model, it can in principle work. I think I haven't done this, but maybe it works. I don't know.
That is a possibility. Another thing, very basic. You see, you have a presence or absence of terms in your histograms. Maybe there is some pattern, something. If you are lucky, something. If I have so many terms which are absent that matter, maybe that is an indicator of possibly bad performances or whatever else. So.
Yeah, and it's also possible to link this to some of the heuristics, like say for example, RLM term distribution, right? So you know that okay, so this is something that we can trust that this measures the correlation between your query terms and the other terms in your top set of documents. So if these explanations are kind of consistent with the RLM weights, then you believe that, okay, so maybe this query was good because it offers a consistent explanations with respect to RLM. Whereas if for some query, the fidelity is low or the consistency is low, then probably you know that the top set is not that good.
Yeah.
So consistency with respect to a top set of documents could be a useful heuristic to come up with a QPP score.
Yeah, who knows? So guys, this little brainstorming between Debasis and me, it's a perfect example of what you can come up with for a master thesis or even a PhD project together. It's not that you need all the answers that you discuss and you try to discover what makes sense, what your intuition suggests. And as you see, there is a lot of possibilities. There is a lot of ramifications. You can say more on explainability itself. You can link it to fairness. You can link it to query performance prediction. So it is a very broad area which all revolves around understanding what our machines do, and it is really hot area, both from a research point of view, because it is the current frontier of research, but also from an industrial point of view, because all the companies need to understand what they are doing and why. And also, as the question of your colleague was implying, then you have ethical teams, teams like accountability, etc. So it's really a great area. And so doing an internship or a thesis on these topics would be very good. Debasis is a leader scientist in the area. University of Glasgow is one of the strongest universities in Europe and worldwide. Okay. Any other questions? Curiosities? Also at home? Let me check. Okay, so Debasis, thank you so much again.
Thank you. Thanks a lot. Bye-bye.
And okay, then the Debasis will send the link to his slides.
Yeah, I'll send you the slides as well. I'll send you the slides. Yes, I'll do.
Okay, and I will share them with you. Okay.
Thank you. Bye-bye. Bye.
Bye.